In this video, we're going to be introducing 4-stroke spark ignition engines, and another name for a spark ignition engine is a petrol engine. In later videos, we'll be discussing compression ignition engines, which are also referred to as diesel engines. But for the purpose of this video, we're going to be focusing on spark ignition petrol engines. So we're going to start by looking at the names of each of the components within a cylinder. And note that in a spark ignition engine, there's usually more than one cylinder. We're then going to briefly discuss the 4 strokes in the cycle and how rotational energy or power is produced from the energy contained within the fuel. We're then going to look at some pressure volume diagrams for something called the Otto cycle, and the Otto cycle is used to represent spark ignition engines. And finally, we're going to discuss some different ways of evaluating the cycle efficiency. So first of all, we have the names of the components within one given cylinder. So the diagram shown here is for a 4-stroke spark ignition engine, and the diagram has been borrowed from Mechanical Engineering blog, and I've provided the URL for that website alongside the diagram. So many of the components here you'll be familiar with, because we've already looked at this type of arrangement in the Mechanical Principles unit. First of all, at the bottom we have our crankshaft, and it's the crankshaft that's going to rotate when the piston moves up and down within the cylinder. Connecting the crankshaft to the piston, we have a connecting rod. So above the piston, we have our combustion chamber. And it's named the combustion chamber because that's where combustion takes place in order to produce power by forcing the piston back downwards. So as the piston draws backwards, we can draw air-fuel mixture into the combustion chamber. And when we're eventually ready to exhaust our combusted air-fuel mixture, the exhaust valve will open in order to allow the exhaust gases to be removed. Right at the top we have the spark plug, and the spark plug provides the spark in order to cause combustion. This is a critical component within a spark ignition engine because it's that spark that causes the combustion process to take place. So next, let's discuss the 4 strokes in the cycle. So the first stroke is intake. Now intake occurs when the piston is drawn backwards, and as it's drawn backwards, our intake valve is going to open. Note that being drawn into the cylinder is a mixture of air and fuel. So we're going to have a large volume of air and a small volume of fuel, but they're pre-mixed before they enter the combustion chamber. Also note that when the air-fuel mixture is being drawn into the chamber, the exhaust valve must be closed. So the piston retracts. As the piston retracts, the air-fuel mixture is drawn into the chamber. The next stroke in the cycle is compression. Now we don't want to ignite that gas until it's placed under pressure. So during this stage, the crankshaft is rotating, the piston is being pushed forwards, and we're seeing a reduction in the volume of the air-fuel mixture. Once we reach the minimum volume, we're ready to ignite that air-fuel mixture. So we move on to our power stroke. Now during the power stroke, we have a number of things happening. First of all, the spark plug ignites the air-fuel mixture. The air-fuel mixture is going to rapidly expand, and as it rapidly expands, it forces the piston head downwards, which is going to drive the crankshaft round. Now once the piston reaches the bottom position, we can then exhaust the gas. And exhausting the combustion gas takes place when the piston head moves forward for a second time. The difference this time is that the exhaust valve is open, which we can compare to the compression stroke because on the compression stroke, both the intake and exhaust valves are closed. So as it states under the diagram, during the exhaust stroke, the piston pushes out the burned gas or the combusted air-fuel mixture, and that's done when the piston moves forward. So what you'll note here is that the reason it's called a 4-stroke engine is because there's 4 strokes. But the 4 strokes are 2 downward strokes and 2 upward strokes. We have a downward stroke when we draw air into the cylinder. We have an upward stroke when we compress the air-fuel mixture. We have a downward stroke when we produce power due to the rapidly expanding air-fuel mixture. And we have an upward stroke when we force the combusted air-fuel mixture out through the exhaust valve. Note that some of the power from our power stroke must also be used to compress the gas. So not all of the power generated on the power stroke is going to produce shaft power because some of that is going to be used in the compression of the air-fuel mixture. So next, let's consider PV diagrams or pressure volume diagrams for the Otto cycle. And as we do this, we're going to discuss some of the assumptions that this makes. So once again, in the top right hand corner, we have our 4 strokes. And we can see how this relates to our pressure volume diagram in a moment. The first stage of the Otto cycle then is moving from positions 1 to 2, and this is known as reversible adiabatic compression. Now all adiabatic means is that when that compression takes place, none of the heat is lost to the surroundings, so the compression needs to take place very quickly. As we know, when we compress a gas, the volume decreases, the pressure increases, but we would also see an increase in temperature of the gas. However, the assumption here with it being adiabatic is that none of that heat is lost to the surroundings, and we can make that assumption because the compression takes place very quickly. The other assumption with this being reversible is that if we was to allow the gas to expand again, the temperature would be the same as it was originally. The second stage in the Otto cycle is as we move from 2 to 3. And from 2 to 3 we have constant volume heating. Now the assumption that we're making here is that when the spark plug fires and heats the air-fuel mixture, the temperature of that air-fuel mixture increases before the piston retracts. So we're assuming that that happens instantaneously, or at least near instantaneously. We can see from our PV diagram that we have a fixed volume because we're moving directly upwards. The volume is unchanged, but the pressure is increasing. Now the reason the pressure is increasing is because the gas is being rapidly heated, so we'd have a build-up of pressure in that cylinder. So next, moving from 3 to 4, we have reversible adiabatic expansion. Now reversible adiabatic expansion once again assumes that no heat's lost to the surroundings, and what we're seeing is the pushing back of that piston head. So this is the second stage of the power stroke, if you like. The gas is rapidly expanding and forcing the piston back down the cylinder. Now for the very last stage, we don't see a change in volume because what we have is constant volume cooling. So if you can imagine, at the end of the exhaust stroke, we're forcing all of the old air-fuel mixture out and we're drawing in a fresh air-fuel mixture. So 4 to 1 is a combination of the exhaust and the intake stages, because in effect, for simplicity, we're assuming that the combusted air-fuel mixture disappears and is replaced with fresh air-fuel mixture at the same volume. So we can see that we are having to make a number of assumptions in order to produce a pressure volume diagram for this cycle. So finally, we can consider how we would go about evaluating the efficiency of this cycle. Now there's 3 different models we can use. The first model is called the Carnot efficiency. Now the Carnot efficiency assumes that we have an isothermal process. And for a process to be isothermal, we need to assume that the temperature of the heat source remains unchanged. What that means is when our spark plug provides the heat, the temperature of that spark plug remains constant. And that can be achieved in other cycles, but not necessarily in a spark ignition engine. So the Carnot efficiency represents the absolute maximum amount of energy for any heat engine. And there's lots of different heat engines in lots of different applications. The internal combustion engine that we're looking at here is just one example. Another efficiency we can calculate is called the ideal Otto efficiency. Now, the ideal Otto efficiency relates to the PV diagram that we saw previously. We're assuming that we have reversible adiabatic compression and expansion stages, and we're also assuming that the heating and cooling of the gas occurs at constant volume. Once again, these are assumptions, but they do lead to inaccuracies in our calculations of efficiency. Now, the third way of evaluating the efficiency of an engine is using engine performance data, and that would represent the actual efficiency of the engine. So in the next video, we're going to take some typical engine data and some temperatures of the air-fuel mixture at different stages in that cycle, and we're going to look at how we go about calculating each of these efficiencies. So to summarise, in this video, we've looked at the names of the different components within the cylinder. We've discussed the 4 strokes that occur within a 4-stroke spark ignition engine. We've looked at the PV diagrams for the Otto cycle that relate to spark ignition petrol engines. And finally, we've looked at 3 potential different methods for evaluating the efficiency of heat engines and internal combustion engines.